And what we want to find is, we want to know what is its molar mass. That's what we want to come up with. So the method that we use, and we can use, the reason we like osmotic pressures, or even actually any one of the freezing point depression, boiling point elevation, the simple tests we can do with the sample to find a rough idea of what the molar mass of it is without doing a whole lot of complicated stuff. What they did with this, benzene. The freezing point depression was 0.240. Sorry about that. Not an osmotic pressure. It's freezing point depression. Sorry about that. Osmotic. Freezing point depression. Sorry about that. Stop that. It's freezing point. Either one. You can actually do it with osmotic pressure too. So they take this sample, human hormone, isolated 0.546 grams. They take it, they drop it in 15 grams of benzene, make a solution out of it. They measure the freezing point, and the freezing point dropped by 0.24 of a degree. Since we're doing freezing point problem, we should look up the Kf value for benzene. Kf value for benzene is 5.12 degrees Celsius. Given that amount of information, we can find the molar mass of this material. Think about it. Pretty easy to do. You have your sample that you extracted. You take it, you put it in a known solvent, dissolve it, and you measure when it freezes. You know when benzene normally freezes. Now you measure it with this stuff in it. You got a new temperature. We can use that to quickly find the molar mass. Delta T out was the molality Kf. If I have Kf and I have delta T, I can find the molality of that solution.
You
The
don't
other
need-
two numbers.
No need to put in the I for this one?
Nope. Molality is delta Tf divided by K sub F. We substitute in what we know. Delta Tf is 0.240. Kf is 5.12. You see, degrees centigrade go away. The molal becomes the unit that comes out of the expression. The molal of this is 4.69, 10 to the minus second. And remember that it's molal, but that we could also write molal as moles per kilogram. They're equivalent. Moles of the solute, kilogram of the solvent. So we found out what the molality, what the strength of the solution is that we made. Now we can find the molar mass. Since molality equals, as we have here, moles per kilogram solvent, we just found the molality. We know how much of the benzene we put it in. So we have two values. We can solve this for how many moles of it do we have. Moles. Now be careful when you do this because you have the molality you just found, 4.69 times 10 to the minus second. your benzene that you dissolved it in, the kilograms of the solvent, was given right here, but it's 15 grams. So make sure when you put it in kilograms. We have 0.015 kilograms. You have about 7.04 times 10 to the minus 4 moles of the material. Finally, moles equal the grams divided by the molar mass. Well, I just found the moles here. The grams are how much of the hormone did we put in? It was given to us up here. We can solve for molar mass. Molar mass. Now, when we do this, because this was a hormone that was introduced, the molar masses tend to be on the much higher than the normal side that we see. So molar mass is 776 grams per gram. Now, this technique that's described in this problem is one that is used a lot in labs that synthesize or find materials that do a lot of the natural product work, because it's easy. If you have a very small amount of your sample, you know where benzene freezes, you take your sample, you make sure it dissolves in it, you apply the equation that we have here, we know how far the temperature dropped, we know what benzene normally freezes, we know its new temperature, find the difference in that. You can quickly, in 3 calculations,